Hi, everybody. I would like to thank the organizers for giving me the opportunity to give a live talk, and also thank you to all of you for coming here on a Sunday afternoon. I'll try to do my best. I've not tried this mix and match format before, so if I make any glitches, I apologize for that in advance. This is based on some joint work with Professor Cato at the University of Chicago. The preprint is on arXiv. And some of the other stuff I'm going to mention is from two of my papers on degree P extensions. Okay, so let's get started. Okay, I thought I would put a silly cartoon here. I hope you can see this. Not sure.
See what?
I went to the next page, but this is frozen for some reason.
No, I can't see the next page.
Oh, good.
Oh, now we can.
Okay, this would have been sad otherwise. Okay, so I think there is a little bit of delay. The main thing I want to point out is that the motivation behind studying arbitrary valuation rings comes from one of the big problems. Right. So defect is something weird that can happen in positive residue characteristic when you start considering arbitrary valuation rings. And that is the main obstacle to local uniformization when you consider the positive characteristic case. Okay. So this is obviously not a complete action plan. I have not solved this, but these are just some of the steps that would hopefully help in that direction. So first I'll talk about what I mean by arbitrary valuation rings by comparing them with the classical setup. Then classical definitions of lower and upper filtrations of ramification groups, a couple other invariants here. The third section is about my results on degree P extensions of arbitrary valuation rings and positive residue characteristic. And the last part is about upper ramification filtration in the arbitrary case. Now, I have tried to reduce technical details as much as possible. So at some time, it might feel like hand waving a little bit, but I will be around on Zulip after the talk if you want to chat about it. Sorry. Okay. All right, so here I made a chart with the notation. We are going to consider valued fields K with valuation V. Valuation ring A sits inside K. These are all the elements with non-negative valuation. Maximal, there's a unique maximal ideal consisting of all the elements with strictly positive valuation. I will explain the conditions in classical and arbitrary case in a bit, but let me explain this notation. We want to consider finite Galois extensions. I'm using n greater than 1 to make sure it's a non-trivial extension. B is the integral closure of A inside L. This also turns out to be a valuation ring because of some nice conditions that we have here. And we have a similar structure upstairs. W is extension of this valuation V. And in both these cases, it will be a unique extension, mainly because in both cases, you have the Henselian property. Okay. In each case, we have residue fields here. Small k denotes the residue field for capital K, and similarly, you have small l over here. Now, if you look at the next row, the third row here, ramification index EL over K, you might have seen this definition before. If you have not, roughly speaking, this is going to measure the change that happens in this valuation when you go upstairs. And inertia degree, this is another invariant of ramification theory that measures the change that happens here in residue fields. This is the degree of the extension small n over small k. Now, when I say classical case, I mean complete discrete valuation rings with perfect residue fields. So basically, you're looking at these local fields of this form with x adic valuation. So valuation of x squared would be 2, for example. This is the valuation ring, and the maximal ideal is generated by element of valuation 1, that is generated by x. Okay. So a few nice things that do happen in the classical situation are listed here. Degree of the extension happens to be equal to the product of ramification index and the inertia degree. Value group here is Z. Z is awesome, but two important properties that we want are it is rank 1 and ideals are principal in this case. If you look at any ideal in this valuation ring, that ideal is going to be principal, and you can look at the corresponding valuation, like for the smallest valuation that is present in that ideal. And that property is coming from the discreteness of C here, and also the rank 1 situation. Okay. And the third property is that the upstairs valuation ring has a very nice description. This is generated by a single element as an A algebra. Okay. So as soon as we start considering arbitrary valuation rings, one by one, these properties go away. So when I say arbitrary during this talk, I mean the only assumption on the valued field K is that K is Henselian. That's it. So the residue field can be imperfect. Value group can be completely arbitrary. We don't have any nice conditions like rank 1, discrete, etc. So if you look at the first property now, there is an extra factor that can pop up. That is called the defect, denoted by D all over K. The defect is trivial in characteristic 0, the residue characteristic 0. So we say that characteristic 0 case is defectless. If you are in characteristic P, this will be some power of P. It can be trivial in some cases, but it can also be non-trivial. And this is basically a huge can of worms that causes all the problems. Okay. And regarding second and third property, as I said, arbitrary value groups are possible, and you no longer have a nice description for the upstairs valuation ring B. Okay. I've given a couple of examples here. They're both Artshare extensions, degree P extensions here. Later, I want to focus on degree P extensions. So these are basically very nice to look at. Okay. So example 1 is the classical case. You have a perfect residue field, etc. This is the Artshare equation, alpha P minus alpha equal to 1 over X. The ramification index in this instance is going to be P, inertia degree 1, and defect would be 1. So this is an example of a defectless extension. If you look at the second example now, I started with the field I had in 1 and then start attaching P power roots here. Now, if you look at the same Artshare equation and the field given by that, it turns out that this extension has defect. There is no extension of valuation, there is no extension of residue fields, and the value group in this case is not discrete. Later, if we have time, I want to come back to these examples. That's why you see some extra space here.
Just so you know, sort of highlighter. I can't. We are not seeing if you have writing. If you have been writing anything, we have not been able to see it. If you were pointing at things, it's a little bit hard to see where the pointer is. But the slides look great, so you can just keep talking over the slides.
Okay. Okay, yeah, there's supposed to be like a pointer. I'm not writing anything extra right now. But...
I see. Yeah, so the pointer is hard to see. So if you can just sort of like describe where you are referring to, that's great. Thank you.
Okay, thank you so much. All right, so far we have understood that defect is bad and we want to deal with it by considering degree P extensions later. So let me review a little bit of ramification theory. You can ignore any definitions that you find too technical. First, I'm going to talk about lower filtration. In this corner, you see complete discrete valuation rings with K perfect. So again, keep in mind the example of local fields. You will see this in a second once I finish writing. Okay. So this is the example you're dealing with exotic valuation. Now you look at elements of the Galois group, sigma, and define this filtration. You look at action of sigma minus 1 on elements of the ring B. Let me try using a mild color to highlight. Hopefully you will see that in a bit. Okay. Okay. All right, so here you see action of sigma minus 1 on elements of B.
Great, that we can see.
Okay, perfect. So depending on what power of the maximal ideal you're looking at, you can define a filtration. This is called a lower filtration. It's indexed by integers bigger than or equal to -1. And this starts with G over here. This is a nice subgroup. The next level is inertia subgroup. Keeps decreasing. So at some points, the like GI might be equal to GI plus 1, but it is going to keep decreasing and eventually it stabilizes at the trivial group. Okay. We want to focus on pieces that are not equal. These are called breaks in the ramification filtration. These breaks, the corresponding values of I, they encode some valuable information. And precisely, these are going to be the breaks you see in blue. Okay. You again see the presence of sigma minus 1 here when you're looking at minimum of whatever valuation. So this particular thing is going to pop up later. Now, if you look at this line over here downstairs in blue, lower filtration is adapted to subgroups. We also want to deal with quotients, and there is a definition of upper filtration via something called Hasse-Herbrand function. You don't need to look at this. I'm not going to use this definition over here. The main thing we need to remember is that you're using values, real number values here. Lower filtration is indexed by integers, and here you're using real number values. There is a famous theorem of Hasse and Arf that says that for abelian groups, G, jumps in this upper filtration are all integers, which is pretty cool. Sorry, this is stuck a little bit. Okay, so I'm going to talk about two important invariants, which I want to generalize later. We saw this particular quantity, valuation of sigma b minus b over b. If you take the minimum of that, we are allowed to do that because we are using the value group C. That minimum is denoted by J sigma. This is called the log Lefschetz number. Important part here that we want to use later is that for degree P extensions, this definition doesn't depend on choice of sigma. Sigma can be any non-trivial element of your Galois group that is going to generate your entire Galois group. And this number does not change if you change sigma. And if you relate this to what we had before for lower filtrations, these J sigmas are the breaks in ramification filtration there. Now, a related invariant is Swan conductor. This is the general definition for a certain representation. You can see that it is related to J sigma. You can ignore it for now. This is just for the sake of completeness. Mainly for degree P extensions, this is a really nice relationship between Swan conductor and J sigma. Remember that these are the breaks in lower filtration, and Swan conductor is related by this particular number P over ramification index with J sigma. Nice thing is that these definitions work even when small k, the residue field, is imperfect, as long as you are in the DVR case. I could say more about this, but I don't think we have time. So I will go to generalizations now. I will just make a small remark that if you consider the case where small k is imperfect, then Swan conductor becomes the jump in your ramification filtration. For degree P extensions, you have a whole bunch of pieces equal to G, and then suddenly you jump to the trivial group. That's the only jump we have. And that break happens at this Swan conductor. So these are results from my two papers. One is on Artshare extensions, and the other one is about mixed characteristic case. Sorry, this is stuck. Okay. Okay. I'm only going to show you results for Artshare extensions because the formulas look nice enough, and we already had examples about those. Analogs are available for mixed characteristic case. Okay. So just to recall, the only assumption on K is that K is Henselian. I'm looking at an Artshare extension L over K. So we have a degree P extension here, non-trivial Artshare extension. So this is going to be given by equations of this form, alpha to the P minus alpha over to F, where F is coming from the field K. So the strategy here is, it sounds very simple. We just replace numbers by ideals and hope things work out the way you want them to. The number J sigma is now replaced by elements of a similar form. So in the classical case, if you look at the ideal J sigma, it is going to be generated by elements that have valuation equal to J sigma, the number. And similarly, H is generalization of our Swan conductor. Now, if you look at the definition of H, it might look a little weird. So I want to point out that if you start with this Artshare equation and change F to another element of K, okay, so you're still not seeing this, I guess. Okay, so if we change F to F plus H to the P minus H, then we don't really change the extension. So you want to consider all possible Fs that give us the same extension, L over K, as an Artshare extension. It's still stuck. Okay. So one of the main results in the first paper is that J sigma is principal if and only if L over K is defectless, so that extra factor does not pop up even if you have arbitrary valuation. And that is equivalent to saying that this ideal H is principal. And it will be given by best F. Then I don't have enough time to discuss the notion of best F right now, but we don't need that right away. The second theorem generalizes the connection between Swan conductor and the number J sigma that we had earlier. You take norms of all the elements of J sigma, consider the ideal generated by that, and you end up with this. I've computed these two objects here corresponding to example 1 and 2 so that you can go back and look at them at a later time. One quick thing you can see here is that in example 1, when we had a classical situation, we had principal ideals, and in example 2, these are going to be infinitely generated, so unions of principal ideals. Sorry, this is still not going to the next page. Are you still able to hear me?
Yeah. Maybe 1 or 2 more minutes.
Yeah, this thing is stuck, so I'm gonna try and just say things, I guess. And then I'll upload the slides.
That works.
Okay. All right, so the next part was supposed to be about a ramification filtration in the arbitrary case. What we did was, don't try to read the preprint, it's too complicated. But the main idea again is replacing numbers by ideals. So if you look at filtrations in the DVR case, like the classical filtration I described and the filtration by Abyss and Saito, we used numbers to define these filtrations. So in the case of Abyss and Saito, they index things by positive rational numbers. We are going to replace those by ideals of a certain ring. We want to describe the upper ramification filtration of the absolute Galois group of a Henselian valued field K. So we consider ideals of integral closure of A inside K bar and define a filtration using that. I've written basic properties and the definition of the filtration on the slides, which you will have soon. A couple of interesting results that we found are we have a generalization of the fact that Swan conductor equals ramification breaks for degree P extensions. So the ideal H that you're seeing on the screen right now, that is going to become like the new break in degree P situation. You can read the details here again. Another interesting theorem is that if you have a defectless finite Galois extension, regardless of its degree, any break in its filtration is going to be a principal ideal. So defectless corresponds to principal. Theme is sort of present there, of course. And my current project is working on the converse that if all the breaks are principal, then your extension has to be defectless. Okay, I'll stop here. Thank you very much. I'm really sorry that you can't see the last two pages, and I'll upload them soon.
Thank you.